People like to sit so high up. Okay, what questions do we have this morning? Maybe online? Okay, let's go on to section 5.3 then. So most of this stuff is just continuation of what we've been doing, but we're going to get some more sort of integration rules, and we're going to think about it more as area under curve instead of limits of Riemann sums and that sort of thing. So we're going to kind of move away from all the rectangles for a little while and just think about finding areas. Okay, so a few things, just some geometric stuff. So any continuous function is integrable. So, i.e., if f of x is continuous on a b, then the integral from a to b f of x dx. Have I used this notation? We have, okay. Is the area under the curve from a to b, and it's equal to the limit of the right-hand sums or the left-hand sums of any of that stuff as n goes to infinity. The sum, let's go k equals 1 to n. B minus a over n, that's the width of each rectangle. And the height, I'm just going to pick the left-hand endpoints. No, I'm going to pick the right-hand endpoints because that's the easier formula to write down. So a plus b minus a over n times k. So this is the width, this is the height, right? That's the area of one of the rectangles, add up n of them, and if I take the limit as n goes to infinity, that's going to give me the area under the curve. I can erase those underlines because they're not actually part of the formula, but there we go. So that's true for any continuous function. There's some other classes of functions that we can do this with, but continuous is kind of the most general. If you have a finite number of discontinuities, then you just break it up into the continuous parts, and each of those parts is integrable, so you can add them together and get the area under the curve. the weird part is when you have infinitely many discontinuities, and sometimes those are integrable, sometimes they're not. It just depends on the function. So let me give you an example of one that's not integrable. It's a function that we've seen before. So we're going to have a whole bunch of dots up here at 1. You have a whole bunch of dots down here at the zeros. This is really discontinuous. And f of x, this is equal to 1 if x is rational, and 0 if x is irrational. This thing is not integrable on any interval. This is not on any interval. Well, if you think about it, let's take an interval here. We need the lower sums and the upper sums to kind of converge on each other to be the same. Like, it's supposed to be the fact that if I take any point in there and I take more and more rectangles, I get closer to the area under the curve. So any rectangle I draw in here, there's a maximum point up here at 1, there's a minimum point down here at 0. So if I take the low intervals for all of those rectangles, my areas are going to start going to 0. But if I take the upper side, I'm going to get these intervals going to the length of the interval times 1. And so because those two things could happen in this limit, the limit doesn't exist, because when limits go to two different things, we say they don't exist. Does that make sense? So this is kind of like the integral case of the sequence 1, 0, 1, 0, 1, 0. This sequence doesn't converge because it just keeps bouncing around. This is the area case of that bouncing around type thing kind of deal. Okay. All right, enough of that. So let's talk about these and why they're just sort of obvious area-wise if we've got some intuition about area. So the interval from a to b, f of x dx, is equal to the negative interval from b to a, f of x dx. That's maybe not obvious area-wise, but it sort of makes sense. What does it mean to have a negative area? Well, in the picture, here's A, here's B. And if I'm trying to find this area here, and I start drawing rectangles, I'm thinking about the width as being positive. If I move in this direction, that's a positive change in the width. Well, if I'm moving in this direction, it's a negative change in width. And so that minus sign, if I go backwards along the interval, I get the opposite of the area. And this allows us to do some nice things with the boundaries here. And I'll show you those coming up. But if I go from A to A, f of x, what should the area under the curve from A to AB? I start here and I stop there. How much area did I go through? 0. Yeah. So the interval from A to A is 0, no matter what the function. As long as the function is integrable, we'll say that. But this is probably true even if it's not integrable, because it just doesn't make any sense. This one's true. This top one's true if it's integrable. This one's true for any function, basically. There's some issues with defining what it means, but A to B, C f of x dx, constant times A to B, f of x dx. So every rectangle I draw is C times as tall. So the area should be C times as big. Okay. I'm only changing one direction. I'm scaling up one direction by a factor of C. And so the total area is going to get scaled by a factor of C. Okay. I'm only scaling the height. You guys have seen that if you scale multiple directions by the same stuff, you multiply by the dimension of the object, like the area of a square. If it's 1 by 1, it's just 1. But if I multiply this direction by C and this direction by C and get a C by C square, I've scaled 2 directions. And so I have to scale the area by a factor of C squared, right? Or if I'd scaled this by B and this by C, the area turns into a factor B times C bigger. Okay. If it's 3 dimensions, you have those 3 scaling factors that you have to deal with. And maybe that's a D. So you have 3 dimensions that you have to deal with, so you have to multiply by all 3 scaling factors. But in this, we're only scaling the height by a factor of C, so the area gets scaled by a factor of C. The width doesn't get scaled. Okay. Integral a to b, f of x plus or minus g of x. I think I've written this one down before, dx. This is the integral from a to b, f of x dx plus or minus g, integral a to b, g of x dx, right? I can split up addition or subtraction into 2 different integrals. Picture there, here's f, here's g. F plus g is going to be up here somewhere. Right. And it turns out that if I take this area should be the same as the blue green area. I didn't draw things very well, but if you put f on top of g, the area that's under f should be on top of the area that's under g after you add them together. Does that make sense? This height should be this height. This height should be this height. So all of these rectangles should get stacked on top of the g rectangles, and then we just add the areas at the end. That's kind of the idea. Subtraction the same way. If I was to subtract them, then these rectangles would be down below, and I'd take it off, and whatever this would be f minus g. Okay, this is the one that uses that first one again, where the minus sign sort of comes into play. So I have the integral from a to b f of x dx. Let's draw a picture here. I'll find this area. And then I have another c value somewhere. Maybe c is right here. I could take the area here plus the area here to get the area from a to b, right? Okay. So this is equal to the integral from a to c f of x dx plus the integral from c to b f of x dx. And that's for any c. C doesn't have to be in between a and b, actually. So let's draw one where c is outside a and b. Let's go with c is over here, right? So if I take the integral from a to b is what I want, well, I can take the integral from a to c, which that's sort of a backwards because a is over here and c is over here. So this would be a negative area because it's got the backwards bounds. And then the c to b area would be this area. So if I take the big area plus the negative area here, I'm end up with just this area. Does that kind of make sense? Same way it happens if you have c over on this far side too. It all works out no matter where c is, as long as we sort of sign that area depending on what my bounds look like. This function, this equation identity is a really nice identity to work with. If m is the minimum f of x takes is, let's say if m is less than or equal to the min of f of x for a less than or equal to x less than or equal to b. What does that statement say? Well, m is a smaller value than the smallest value of the outputs of f over the entire interval from a to b. So it's smaller than anything that f of x can be in the interval. So here's a, here's b. There's the minimum. M is anything that's down here. Okay. We're going to have a maximum. We're going to call that capital M. M is going to be anything upper there. Okay. And M is greater than or equal to the max a less than or equal to x less than or equal to b f of x. Then m times b minus a is less than or equal to the integral from a to b f of x dx, which is less than or equal to m times b minus a. Okay, all that says is the yellow area is in the middle between the green area and the purple area. If I take the maximum and I make it a rectangle on A over B, that's going to be bigger than the area under the curve, which is going to be bigger than the area under the rectangle where I take the minimum as the height. Does that make sense? So just geometrically, that's what we got there. And then this one. If f of x is bigger than or equal to g of x for all x in AB, then integral over AB f of x dx is bigger than or equal to the integral over AB g of x dx. So if you got a bigger function, you've got a bigger area. Okay. Here's f, here's g, it's always bigger. Sorry, f is bigger. That's f, this is g. Then that area is smaller than that area. In particular, if g of x is bigger than 0, or sorry, if g of x is equal to 0 and f of x is always bigger than g of x, so f of x is always bigger than 0, then I don't even need to say that. If I have this, then the integral from a to b f of x dx is bigger than or equal to 0. So if you're only taking positive values from your function, your area is going to definitely be positive. Okay. On AB, I want to make sure that A is less than B there, right? Because if B is less than A, then that's not true. It's definitely negative. But if we've got that, we're good. Okay, that's 311 table. We're going to kind of use those things to find areas under curves here. And we're going to have a couple special case things. Some special cases that we've already proven, basically. Integral from A to B of x well, let's do this one first. Of 1 dx, that's equal to b minus a. So your function always takes a height 1. So you're adding up a bunch of rectangles of height 1 over the interval from A to B. So all you have is a rectangle, right? Rectangle's height 1, width is b minus a, so you get the area as b minus a. If I take x, what I get is I get b squared minus a squared over 2. That'd be my area. Why is that? Well, my function's just a triangle now. Triangle has a height there of b and the height there of a, so really these are half squares. So this area is b squared over 2. This area is a squared over 2. And so the area that we're actually interested in, b squared minus a squared over 2. Okay. So how do I know this bit before I knew the triangle? Because I've done this before. But yeah, you want to draw the triangle basically. That's kind of the good explanation of it, but we've got other explanations. We've done the bit in the past on the last homework assignment where we break up everything into rectangles, right? And we drew in all the rectangles and we took limits, and I think we did limits of functions that were just linear before. And so we can do it that way too and get the exact same thing, but the geometry is kind of the easier one to work with in this case. And then in the next section, we get to use the fundamental theorem of calculus, which tells us antiderivatives work. And the antiderivative of x is x squared over 2. And so you get to evaluate the antiderivative of b and subtract the evaluation of the antiderivative of a. And so since the antiderivative of x is x squared over 2, you put in b, you get b squared over 2. You put in a, you get a squared over 2, and then you take the difference. That's the fundamental theorem of calculus. And the geometry on the next one that I'm going to write down doesn't work out so well. So we're just going to write down what the formula is without proof in this case. But we have shown it before. I know we showed quadratics in the previous homework. So this is b cubed minus a cubed over 3 instead of over 2. And so you've got a parabola a to b. And that area will be round. Okay. And that comes from those Riemann sums. And you use the Riemann sums to prove this. And then eventually what you can do is you can kind of prove it for any of the power functions, or you can just prove the fundamental theorem of calculus and then do anti-differentiation and prove it that way. Since proving it for every single power function is a little hard, if you prove this other thing first, it becomes easy. But proving that other thing's not necessarily that easy. Okay, so let's use these 3. So like integrated degree 0 thing, integrated degree 1 thing, integrated degree 2 thing to do some integrals here. So let's try and evaluate. The integral from, man, those are, okay. We'll just do some square root, some book problems. So this is a linear guy. So we're going to take b squared over 2 minus a squared over 2. So I'm going to take 3 minus a squared over 2 in this case. Integral a to a squared. So this is a quadratic, so I'm going to take cubes. So this is a to the 6th minus a to the 3rd over 3. Look at integral pi to 2 pi of just theta d theta. This is linear, right? I don't necessarily have to have x as my variable as long as I'm integrating the variable to the variable, right? So this is linear. This is going to be a squared thing. So this is going to be 4 pi squared minus pi squared over 2, which is 3/2 pi squared. The area between 1/2 and 3/2 of x dx is going to be 3/2 squared minus 1/2 squared over 2, which is going to be 9/4 minus 1/4. That's 8/4, which is 2 divided by 2 is just 1. Let's try something a little harder. Let's try from 1 to 3, 1 plus x dx. What should I do with this one? I can't take one outside, but I can split it up. Right, this is an addition one. So one of these rules up here said, what do we do with addition? This guy says, you've got addition of two functions inside of an integral. You get to do each of the functions inside the integral and add them together. So we're going to rewrite this as the integral from 1 to 3 of, 1 to 3 of 1 dx plus the integral from 1 to 3 of x dx. And that's going to be 3 minus 1 plus 3 squared minus 1 squared over 2. So that's going to be 2 plus 4, which is 6. Questions on that one? Yeah. The first three ones? Yeah, the integral of the constant, the integral of the, yeah, it says in these homeworks, use the equations 2 and 4 to do these. And so, yeah. Or equations 1, 2, and 4, which are the three things that I wrote down. So, eventually, in the next section, we'll be doing the stuff where we actually take antiderivatives and use the fundamental theorem of calculus. But This is mostly just getting you used to those 7 rules that I wrote down up at the top, kind of manipulate things that way. Because I want to do more like this than this. This was just, okay, these 3 rules that we wrote down, how do you use them? Now I want to do stuff like that, which uses those 7 things that we wrote down first. So let's do the integral from -1 to 2 of 3x squared minus 2x plus 7 dx. So how should I do this one? Split it up first. -1 to 2, 3x squared dx minus the integral -1 to 2. There's a minus because that's a minus, so 2x dx plus integral -1 to 2 of 7 dx. Okay, what do I do with the 3x squared? I can move the 3 outside. I can move the 2 outside. I can move the 7 outside. What's left inside if I move the 7 outside? 1. Okay. So now I've got 3 times 2 cubed minus 1 cubed over 3 minus 2 times 2 squared minus 1 squared over 2 plus 7 times 2 minus 1. So the 3's cancel, that's nice. I've got 8 minus a minus 1, which is 9. The 2's cancel, that's kind of nice. And then I get 4 minus 1 is 3. And then I've got plus, the 7 doesn't cancel with anything in this case, but 2 minus 1 is 3, so times 3. So this is going to be 6 plus 21 is 27. Questions on that one? Do the integral from 2 to 1 of 1 minus x t over 2 dt. What should we do with this? We'll split it up. First thing I'm going to do is I'm going to write a minus sign. And then I'm going to integrate from 1 to 2 instead of 2 to 1. And then I've got 1 dt minus the integral 1 to 2 of t over t, and that's going to be times 1/2 dt. So split it up as much as we can right away. Pull constants outside, split up the addition, just leave my function inside t. Are we good with that split? Okay. Now I can evaluate. So I got a minus all this stuff. The integral from 1 to 2 is 2 minus 1. From 1 to 2 of 1 is 2 minus 1. Then I've got minus, I've got a 1/2. I've got a t, which goes to 2 squared minus 1 squared over 2. Close that off. This is a minus. That's a 1 minus 1/4 of 3. This is a minus 1 minus 3/4 is a minus 1/4. Good with that? Okay. Suppose f is integrable everywhere. And what I mean by that is on any finite interval, you can find a finite area for the thing. And the integral from 0 to 3 f of x dx equals 2. The integral from 1 to 5 f of x dx equals 7. The integral 0 to 5 f of x dx equals 8. Let's go the integral from 3 to 5 f of x dx equals 6. Hopefully all these things are consistent. So let's draw some pictures. I've got 0, I've got 3, I've got 1 as one of my boundaries, I've got 5. Okay. Got 4 different areas. So let's use 4 different colors here. Do green for that one, yellow for that one, blue, purple. Okay, 0 to 3. That area is 2. Yellow. 1 to 5. That area is 7. Blue, 0 to 5. This area is 8. And then purple, 3 to 5. That area is 6. And that's good because the purple plus the green should equal the blue. So fortunately, I wrote down the right number. Okay, what's the area? Let's try and find the integral from 0 to 1 of f of x dx. Which areas should I look at to find that? Yeah, I'm going to look at the blue and the yellow, right? If I take the blue area minus the yellow area, I should get the area from 0 to 1. Okay. So if I can look at which of my boundaries I have, this is going to be the integral from 0 to 5 f of x dx minus the integral from 0 to 1 f of x dx. That rule, which of these rules up here was that? Sorry, 1 to 5. Which of those rules is that? There's my rules. Yeah, this one. We're putting C in the middle and we're splitting it up. Okay, so down here, the full interval is 0 to 5. 1 is put in the middle, and we split it up. So it should be 0 to 1 plus 1 to 5 is 0 to 5. But we moved one of those over to this side and put a minus sign on it, right? So we're using the rule that 0 to 1 f of x dx plus integral 1 to 5 f of x dx equals the integral from 0 to 5 f of x dx. And then we're moving this guy over to this side so we can solve for that. Okay. Are there other areas here that we haven't written down that we could actually find? Yep, 1 to 3. Sorry. How would I find that one? Couple ways now. We could use the green and the one that we just found. Yeah, we can use the green and the one that we just found. So this is the integral from 0 to 3, which we have written down as green, minus the integral from 0 to 1, which we just found. And so this was, green was 2. This one that we just found was 1. We didn't actually evaluate that, did we? This is equal to 8 minus 7, which is 1. So this is minus 1. So this is also 1. We good with that? What's the other way we could do this? Yeah, we could use the yellow minus the purple. Yep. Integral from 1 to 5, f of x dx minus the integral 3 to 5, f of x dx is the integral from 1 to 3. And so in that case, what did I say? The yellow minus the purple. So yellow is 7, purple is 6. Also 1. Okay. Good with this kind of stuff? All right. There's one more type of function here, or type of question, it looks like, which is an average value function, average value question. So let's write down that again. I think we wrote this down in the past, but the average value of f of x on AB, that's equal to 1 over b minus a times the integral from a to b f of x dx. Right, so you take the area, you divide it by the width, and that's how high a rectangle would be of that same area, right? If you're trying to smooth things out, find the average value, you get that. Okay, so let's try and find the average value of, say, sorry, we can't do cubes yet, 3x squared minus 2x on 2 to 5. So what we're supposed to do is we're to take 5 minus 2, put it in the denominator, take that times the integral from 2 to 5 of 3x squared minus 2x dx. So this is going to be 1/3. And I'm going to break these things up. So this is the integral from 2 to 5 with a 3 and an x squared dx minus a 2 integral 2 to 5 of an x dx. Are we good with that split? Okay. Now I can just evaluate stuff. So this is 1/3 of 3 times 5 cubed minus 2 cubed over 3 minus 2 times 5 squared minus 2 squared over 2. Okay, so I've got 1/3. That 3 and that 3 cancel, that 2 and that 2 cancel. So I've got 125 minus 8 minus 25 minus 4. So this is 1/3 of, is it 96? Yeah. So my average value there is going to be 32. Questions on that one? Okay, so that should get you good and started on 5.3 homework. If you have questions, let me know tomorrow, and I will see you.